The very first topic with most differential equations courses is the notion of separable equations. I think what I'm going to do in these videos is introduce notation as I do problems and such instead of have a separate thing for that. So let's start with this definition. A differential equation is simply an equation with derivatives in it. This course is focused on methods for solving such equations. And so with that in mind, let me start with the very first thing that's usually talked about, and that's differentials. And many times I'll have something like y is a function of x. But then what does this mean? dy. That's the differential of y. The way it's defined is this. dy equals dy over dx, so there's the derivative of y with respect to x, times delta x. Now, for just a moment, let me use the function y equals x. Then for this particular function, dy equals, well, dy over dx would equal 1 delta x. Now, since y equals x, I can replace y in this, and I get dx equals delta x. So really, a fun way of putting this is the following. dy can be defined as dy over dx times dx. So it looks like the dx's are canceling each other, but really there's a lot going on here. What this allows you to do is something we call separate variables. Let me start with an example real quick to show you how it works. So for my first example, I'll say solve, and I don't expect you even know what that means just yet, but typically equations will have derivatives in them, and they'll equal something. All right, now let me go ahead and do my trick. This where I replace with the differential. I can multiply both sides, if you will. So I've done the same thing to both sides. Now let me simplify the right side to put it back to the dy that it was. And right here we've accomplished what's called separating the variables. Y's on one side, x's on the other. So then what I can do at this stage is I can slap an integral on both sides of the equation, and you must understand that eventually an integral is going to be taken on all differential equations to solve them. Now the right side is a pretty simple integral. I don't need to expand it. I'm sure you know that it equals x plus 1 to the third power over 3 plus c, and the left-hand side is equal to y. So that's what I'm talking about in solving them. You're not finding a number, but you are finding a function. The solution to the problem is actually a function, typically. Another example. Suppose I wish to solve dy over dx plus 2x y squared equals 0. So now what I want to try to do is get the y's on one side and the x's on the other. So the first thing we can do is I can take the 2xy squared, subtract it off to the other side. And then I'm going to, if you allow me to use this term now, I'm going to multiply both sides by dx to accomplish the following. Now at this stage, to separate y's and x's, I'll divide both sides by y squared. And at this stage, I'm ready to integrate. I think this left-hand side, I'm going to rewrite it to be y to the negative 2 dy. And the right side, I'll pull the negative 2 out, and I'll get x dx. The left side, of course, will be negative y to the negative 1. And the right side, I'll have negative 2 times x squared over 2 plus a constant. Now technically there's a constant from both sides, but if you'll allow me just to collect all constants on one side, that's usually the way that we like to see it. So I can divide by the 2's. I could then, here's what I have so far, negative y to the negative 1 equals negative x squared plus a constant. I'm going to multiply both sides by negative 1. I'll get y to the negative 1 equals x squared minus c. But really, since we allow c to be a constant of any kind, a general constant, we don't know what it is, I can just put a plus here. C could be negative, for example. And then if I want my final answer for y, I'll take 1 over of each side, and I'll get y equals 1 over x squared plus c. Barring any further information, that's what I know the answer to be. Here, let's see, a little more complicated. Let's have sine of 3x dx plus 2y. We have cosine cubed of 3x dy. Set that equal to 0. Now notice, in some fashion, the separation of variables has already occurred, although I don't have x's with just x's and y's with just y's. So what I'm going to do is I'm going to subtract sine of 3x dx from both sides. So I have 2y cosine cubed of 3x dy equals negative sine of 3x dx. Now I'll divide then by cosine cubed of 3x, and I'll get 2y dy equals negative sine of 3x divided by cosine cubed of 3x dx. Now that I have the variables completely separated, I'll go ahead and slap an integral on both sides. So on the left, I'll pull the 2 out, I'll get y dy. And on the right, I'll leave the negative in there because I'm going to do a u substitution, and you'll see why that might be desirable to leave it like that. Here, the left side is easy. The integral of y is going to be y squared over 2. I'll be able to cancel the 2's, and I'll get y squared. Remember, I'm going to throw my constant in the right side. Now on the right-hand side, I can use a u substitution to accomplish what I want. I can do u equals cosine of 3x, and then du equals negative 3 sine of 3x dx. Or, better yet, negative 1/3 du equals, take out the negative, I didn't mean that. I want to leave the negative with the sign. This way, then, I have a u cubed in the denominator, and the negative actually gets sucked into the du. So it looks like I have 1/3 integral u to the negative 3 du. And of course, that's really straightforward to integrate. I'll get 1/3 times u to the negative 2 over negative 2 plus a constant. So y squared equals negative 1/6. Now, this is 1 over u squared, so, and u was cosine of 3x. So I think I'll put it down here, and I'll get cosine squared of 3x. And then we'll put our constant. And that's good enough. Notice I didn't solve for y explicitly. This is referred to as an implicit solution. That's when we have not solved for y completely. If I wanted an explicit solution, I would have to write y equals plus or minus the square root of negative 1 over 6 cosine squared 3x plus a constant. Notice, I want you to notice something here. Cosine, if it's not 0, cosine squared is going to be positive no matter what. So this piece here will be negative no matter what. So the only way it's going to equal something squared, which cannot possibly be negative, is for that c to be there. So make sure you get that c underneath of the square root. This here are two explicit solutions. And we'll find that I may want the positive or negative one. It all depends on the nature of the problem being asked. Sometimes I'll need to solve for it, sometimes I won't. For example 4, we have dn over dt. And a lot of things will have a dt because time is so important to any kind of real-life problems, especially calculus or differential equations. Time is most always going to be your independent variable. And suppose the other side is n e to the t plus 2. So in this situation, n is like your y and t is like the x. So I think probably what's best is let me subtract this n to the other side. So I'll have n e to the t plus 2 minus n. And on the left I have dn over dt. Let me then multiply both sides by dt. So dn equals n e to the t plus 2 minus n dt. Now, the way I drew this plus 2, it looks kind of weird to me, so let me change this. I want to be specific. I want to be very clear what I'm doing. Now, I can factor out an n. That way I'll be able to separate as needed. I'll pull the n out, and I'll get e to the t plus 2 minus 1 dt, and on the left, dn. Divide both sides by n. So I have dn over n equals e to the t plus 2 minus 1 dt. Now, all this dividing and stuff like that, you've always been told you don't know if you can divide by n because it may be 0. Well, in this class, we'll simply take 0 away as a possible answer and say, well, this is what you got to do to get the answer, and 0 is not possible. We will allow for that to happen. On the right, it looks like I have only t's involved and a number. That's okay. And on the left, I have my n's all together, so I'll integrate. So I get the integral of dn over n equals the integral of e to the t plus 2 minus 1 dt. And this just to show you that you are going to use the same knowledge that you had before. The left side will be the natural logarithm of the absolute value of n, as you should know. The right side, this is easy to integrate. I'm going to get e to the t plus 2 minus t plus a constant. Now, I can take e to everything and then play around with the absolute values, but to be honest, to me, I'll be perfectly happy with this, because if it comes down to having a very ugly equation to get an explicit solution, I think I'd prefer an implicit solution. Now, an additional piece of information could be given to you, and that is the nature of initial value problems. Here, you'll notice all of those problems that I gave you so far has a constant that we can't determine. However, if you know just one piece of information, you can usually determine what that constant is. I'll show you what I'm talking about. So let's do an example. I guess I'll do explicit solutions when I can, and leave them as implicit when I can't do anything more with them. So let's say we give you solve the following equation. dy over dx equals y squared minus 1 divided by x squared minus 1. And then the initial value is given as y of 2 equals 2. Now, the initial value are usually some easy information to get. Our solution will be good for an interval about x equal to 2. What that interval is, we'll talk about that more later. Right now, let me go ahead. I think cross multiplying, I don't know, let me see. I'm going to multiply by dx, but I'll divide by y squared minus 1. So I have 1 over y squared minus 1 dy equals 1 over x squared minus 1 dx. And of course, now I'm ready to integrate. And there's a number of ways you can do this. I'm thinking of partial fractions. And these usually aren't as hard as you think they are. You know, you do the whole system of equations and things like that. But a lot of times you can fudge them fairly reasonably. I know that y plus 1 and y minus 1 are going to be factors. So I'm going to start working it here. And this is the way I think. If I do y, if this was plus, for example, and I added these together, I'd have y minus 1 plus y plus 1. And the 1's would cancel, but I'd be left with the y. And originally I needed just a 1 here. So instead of a plus, maybe a minus is a better thing to use. And so then I'll have y minus 1 minus y minus 1. So I'll have negative 2. So, and better yet, I think I might accomplish what I want better is if I do these. So let's try it one last time. If I multiply, do a cross multiplying kind of thing to put this back to its original format. I'll have negative y plus 1 plus y plus 1 will give me a 2 in the numerator. So I can fix it by putting a 1/2 out there. And I can do exactly the same thing. I know it's the same thing except just different letters. Okay, let me go ahead and integrate. So this part will be negative natural log absolute value of y plus 1 plus natural log absolute value of y minus 1. On the right, I'll get 1/2, exactly the same kind of a thing, negative natural log absolute x plus 1 plus the natural log absolute x minus 1 plus a constant. And I will do much compacting here. You know by your rules of logarithms that I can combine these things. So I have 1/2 the natural log of y minus 1 divided by the absolute value of y plus 1. Same thing goes for the right side. I'll get 1/2 natural log absolute x minus 1 divided by absolute of x plus 1 plus a constant. I can multiply both sides by 2 to get rid of the 1/2, and the c will just absorb that 2. So the natural log absolute y minus 1 over y plus 1, that equals the natural log absolute x minus 1 over x plus 1 plus a constant. Now, you can, if you want to leave your answer that way, you can. Supposing an explicit solution would be required. Let me first take care of this c. We know the initial value was y of 2 equals 2. So when x is 2, y is equal to 2. Let me plug those in. So natural log absolute 2 minus 1 divided by 2 plus 1 equals natural log 2 minus 1 over 2 plus 1 plus a constant. On the left, I get the natural log of 1/3. On the right, I get the natural log of 1/3 plus a constant. Subtract the natural log of 1/3 off, and we'll see that 0 is equal to c. So there is no constant here. So my answer simply can be written as the natural log of y minus 1 over y plus 1 equals the natural log of x minus 1 over x plus 1. Or if you want to, you can take e to the both sides, and I could get the absolute of y minus 1 over y plus 1 equals the absolute value of x minus 1 over x plus 1. Now, suppose we want an explicit solution. That is, we want to solve for y. Well, how can we do that? Whenever you have the absolute value of something equal the absolute value of something else, we have two possible answers. Y minus 1 over y plus 1 equals x minus 1 over x plus 1, or y minus 1 over y plus 1 equals the negative of that, because this is the only way they can both have the same absolute values. So let's start first. When I looked at the initial value, we had y equals 2 when x equal 2. So let's check these both to see what happens. If I plug in y equals 2, 2 minus 1 over 2 plus 1, 2 minus 1 over 2 plus 1, this equation is 1/3 on both sides, so it checks out. Over here, if I try to do that, I'll get 1/3 equals negative 1/3, and I do not want that. So that can't possibly happen. So what I'm left with is this situation here. So I can get, this is a better implicit solution is this. So I can just have y minus 1 over y plus 1 equals x minus 1 over x plus 1. So that is an implicit solution. Now, for explicit, how do you solve it? Probably the fastest way to do this, if I can make, let's see here, we have y minus 1 over y plus 1 equals x minus 1 over x plus 1. Maybe I want to leave x's on one side and get the y's. Maybe I'll keep the y's to the left. So let me go ahead and multiply through by y plus 1. So y minus 1 equals x minus 1 over x plus 1 times y plus 1. So then I have y equals x minus 1 over x plus 1 times y plus 1 plus 1. It's not quite explicit yet because I still have a y on the right hand side. So I'm going to take this fraction and multiply it through or distribute. So I have y equals x minus 1 over x plus 1 times y plus x minus 1 over x plus 1 plus 1. Now I'll go ahead and take this stuff to the left-hand side. So I'll get y minus x minus 1 over x plus 1 times y equals x minus 1 over x plus 1 plus 1. I will factor y from the left. Y times 1 minus x minus 1 over x plus 1 equals x minus 1 over x plus 1 plus 1. And then to get y by itself, I'm going to divide by this whole chunk. So one possible answer looks like this. So there is an explicit solution. You may not like the looks of it. Any kind of a teacher you've had previous probably wouldn't like that look, but it's fine. It is an answer. However, should I want to simplify, note that you can simply multiply the numerator and denominator by x plus 1. What are we going to get? Y equals, when I multiply the numerator by x plus 1, I'll clear out this fraction and I'll be left with an x minus 1. But then I'll have plus x plus 1. In the denominator, I'll have x plus 1 minus x minus 1. Make sure you put those parentheses there. So it looks like on the top I'll have 2x, and in the denominator I will have 2. So this gives me, for a solution, all that leads to the simple solution y equals x. There is my explicit solution. All right, let's see what we have. We have 1 plus x to the 4th times dy plus x times 1 plus 4y squared dx equals 0. So as with anything else, I think I'll subtract the second half of this equation, and I'll get 1 plus x to the 4th dy equals negative x times 1 plus 4y squared dx, and I'll divide by the necessary things to get 1 over 1 plus 4y squared dy equals negative x divided by 1 plus x to the 4th dx. And then let's go ahead and integrate. So on the left I'll get 1 over 1 plus 4y squared dy equals, and on the right I'll pull the negative out. I'll get x over 1 plus x to the 4th dx. So to solve these, they're both similar in a way. On the left side, I am going to let u equal 2y. That way 1/2 du equals dy. This is for the left-hand side. And so I'll get the integral of 1 over 1 plus u squared du, but don't forget this 1/2 out front. On the right side, I don't want to use u. I don't want to use the same variable for both sides. So I'm going to let w equal x squared. And then dw equals 2x dx. Better yet, 1/2 dw equals x dx. So the right becomes negative 1/2 the integral. So x dx, there's my dw part. And then on the bottom, I get 1 plus w squared dw. The reason for doing that is the hope is that you'll recognize that these are both arctangent problems. Now, at this stage, right now, I could multiply both sides by 2 and take that out. So I don't even play with that part. On the left, I'll get arctangent of u. And on the right, I'll get negative arctangent of w. And then I'll have plus a constant. So let me go ahead and change my u and w's back. The u is 2y, so I'll get arctangent of 2y equals negative arctangent of x squared plus a constant. This is fine as an answer, unless I ask you to get an explicit solution. So suppose we were asked to find an explicit solution. That means try to get y by itself. So one way to do that is to take the tangent of both sides. So on the left side, I'll get the tangent of arctangent of 2y. And on the right side, I'll get tangent of negative arctangent of x squared plus a constant. The left side is easy. I'll get 2y. The right side is more complicated because on the right side I have a sum of angles, and maybe you do or maybe you do not remember formulas for a sum of angles. So let's do a little note here. If I wanted to figure out tangent of a plus b, alpha plus beta, I don't personally have this one memorized. So what I'm going to do is rewrite it as a sine of alpha plus beta divided by cosine of alpha plus beta. I do happen to have memorized the formulas for sine and cosine. If you remember, sine goes like this: sine of alpha cosine of beta plus sine of beta cosine of alpha. And for cosine, it goes cosine of alpha cosine of beta minus sine of alpha sine of beta. Now what I'm going to do, this may seem odd to you, but I'm going to factor out a cosine of beta from the numerator and the denominator. That way what I'm left with in the numerator is sine of alpha plus sine of beta divided by cosine of beta times cosine of alpha. I'm going to do the same thing in the denominator, factor out a cosine of beta, and that will leave me with cosine of alpha minus, same kind of thing is going to happen over here, sine of alpha cosine, sine of alpha, sine of beta over cosine of beta. Of course, there's a reason I did that. Besides canceling that part of it, here's what I have so far. in the numerator, I have sine of alpha plus tangent of beta cosine of alpha divided by cosine of alpha minus sine of alpha times tangent of beta. And now I'm going to do the same kind of a trick again. This time I'm going to factor out a cosine of alpha. And the trick will work the same way. Here I'll get a sine of alpha over cosine of alpha. I'll have tangent of alpha plus tangent of beta all over. And the denominator will work the same way. If I take a cosine of alpha out of there, I will be left with 1 minus cosine of alpha, sine of alpha divided by cosine of alpha will be tangent of alpha, tangent of beta. And so I'll cancel out these cosine of alphas. And so my sum of angles formula then, tangent of alpha plus beta, is tangent of alpha plus tangent of beta divided by 1 minus tangent of alpha times tangent of beta. So this is my sum of angles formula for tangent. Now, if you'll recall, we were in the process of solving something. So let me kind of get this out of my way. We had, let me put this back, tangent of negative arctangent of x squared plus a constant. Of course, this probably is not a bad way to leave it. Certainly students have done that. And then just divide by the 2 if you want to get y by itself. But let me go ahead and grab this thing and copy it below. Not where I wanted it, but I don't care. That doesn't mean so much to me. Here, my alpha is like this thing, the negative arctan x squared. My beta is like the constant. So let's go ahead and use this formula that I have up here. And I will get tangent of the negative of arctangent x squared plus tangent of c divided by 1 minus tangent of alpha. So tan of negative tan inverse of x squared times tangent of c. And I can do a lot of simplifying, like tangent and the negative arctangent. You may or may not remember that tangent is an odd function. What that means is that I can pull the negative from inside the parentheses out front. Let me do that. I'll do the same in the denominator. Okay, of course, the reason for doing that is that the tan and the arctan cancel each other, and I'm left with negative x squared plus tangent of c divided by 1 plus x squared times tangent of c. And then I can divide by 2. So there would be an explicit solution. Suppose that In the previous example, we were given the initial value of y of 1 equals 0. If that's the case, then I'll be able to figure out what these things are by allowing x to equal 1 and y to equal 0. So x equals 1, y equals 0. Let's see what happens. Let's plug them in. Y equals 0 when x equals 1, so I have 1/2 times negative 1 squared plus tangent of c all over 1 plus 1 squared tangent of c. Of course, since there's a 0, I can multiply through the 2 easily. Had I known this earlier, I would have done it earlier, but I suppose you didn't know that till now. So multiply through by 2, and I'll get tangent of c minus 1 all over tangent of c plus 1. Multiply both sides by this numerator, and I'll get 0 equals tangent of c minus 1, or if you want, 1 equals tangent of c. I really don't even care about what c was. My solution had tangent of c, so I can put 1s in these spots. And so that will give me my new solution. Y equals, let's see, I'll have 1/2 negative x squared plus 1, or 1 minus x squared divided by 1 plus x squared. All right, one last one for this. Let's say I'm giving you dy over dx equals y squared sine of x squared. And it's an initial condition problem, so you're told that y of negative 2 equals 1/3. Well, let me go ahead and do the normal things. I'm going to separate the variables, and I'll get y to the negative 2 dy equals sine of x squared dx. Then I'll go to integrate both sides. On the left, we have negative 1 over y equals, and then on the right, sine of x squared dx. Now the problem right now that I have is there's no elementary solution for this. I mean, I don't have an arc or an antiderivative of sine of x squared. One of the things you could possibly do is go to an infinite series and work that maybe, but that is arduous and not at all desired. Plus, at some point, how do I plug in negative 2 for x? I mean, I can't plug it in here. I have to integrate before I plug anything in. I guess I put the 3 in for y, but as of yet, there will be a constant out there, and maybe it'll help. But this, I don't know. I'm stuck. So, I have a little trick to handle this. Let's come back to this right here. And as a matter of fact, let's come back to this right here. Let me go ahead and have this, the original equation. So we have dy over dx still equals y squared sine of x squared. What I'm going to do then next is this. Dy over dt equals y squared sine of t squared. You'll see in a minute why I'm going to t, because t will be a variable that I'll use in integration, and what you use in integration doesn't really matter. Then what I'm going to do next is multiply both sides by dt. dy over dt times dt. Same with the right, y squared sine t squared dt. Notice I'm not canceling or anything like that. I have a reason for that. I'm going to plug or divide by y squared, and I'll end up with y to the negative 2 dy over dt times dt equals sine of t squared dt. Now, I want you to think about something. We were given as an initial value y of negative 2 equals 1/3. Remember the initial value, IV, y of negative 2 equals 1/3. Check this out. What I'm going to do in my next step is I'm going to integrate from negative 2 to x, y to the negative 2, dy over dt times dt, which I have to do exactly the same thing on the right. Negative 2 to x sine of t squared dt. Okay. Now the left-hand side is not hard to integrate, especially if you think of y as an f of t or something like that. So as an example, set u equal to, this may sound horrible to do, du is equal to y. So then du equals dy. But if it's over t, and so in this format, it's difficult to see what I'm up to. It really is. So I don't want this stuff. Instead, let u equal y. But all right, the reason I'm doing this is because think of y as an f. This is f prime. Du is going to equal f prime of t dt. So let's take a look at our integral from negative 2 to x. So I'm going to put it in there. F of t to the negative 2. This part here is f prime of t dt. Okay, but that's u. I have u to the negative 2. This stuff is du. On the right, I can't integrate it, so I'm going to leave it be for the time being. Okay, so the left side will go from negative 2 to x, and I'll have u to the negative 2 du, which is easily integratable. And in fact, when you do this, I forgot to change my limits of integration. When 2 or t equals negative 2, I have f of negative 2. And then when t is equal to x, this is an f of x. Actually, I know that f of negative 2, since f is the same as y, f of negative 2 equals 1/3. So I'm going to do one last thing. 1/3 to f of x, u to the negative 2 du equals the integral from negative 2 to x sine t squared dt. Then the left side, when I integrate u to the negative 2, it'll become u to the negative 1 over negative 1, or negative 1 over u. And I'm replacing that with 1/3 f of x. On the right, negative 2x sine t squared dt. Now, since these are definite integrals, I don't have to worry about constants. Then I will replace the u, of course, with these values that I have. I have negative 1 over f of x, that's y, plus 1 over 1/3, that's the integral from negative 2 to x, sine of t squared dt. This part, of course, is equal to 3. So I'll get negative 1 over, I don't know why I put f of y, that's an f of x. I'm going to change now back to y to make life easier here. That's going to equal the integral from negative 2 to x sine of t squared dt minus 3. And then for my last step, I'm going to simultaneously reciprocate and divide by negative 1. And so I'll end up with y equals 1 over 3 minus the integral from negative 2 to x sine of t squared dt. This is the best you're going to be able to do because I cannot integrate that integral. You can throw it into a machine to give you answers for each individual x that you plug in. This is a function of x. Notice that when I change x, this will change the value of this integral. T is what they call a dummy variable, so it's not that important. Anyways, there is a solution. Since I could not integrate this, I have to leave my answer in this format, and I am done.